Hello, my stats friends. So this is our lesson on 4.3, using studies wisely. It's going to kind of be the end of this chapter. It's going to put some thoughts together, and it really is going to kind of preview some inference ideas that are coming up later in the year. But because we've started with chapter 4 and we got to go back and do chapters 1, 2, and 3, there's going to be a couple of pieces here that are going to feel muddy to you when we leave this lesson. Don't panic. We are definitely going to come back and revisit these topics and build up as we learn some more things throughout the year. So, this is adapted from the 6E edition of Tabor and Starnes and Tabor's Book of Understanding Statistics. If you're a teacher out there looking for the right thing, by no means do I have everything down pat, but this is where it's from. All right, so inference for sampling. So when members of a sample are selected at random from a population, we can use that sample results to make inferences about the population. Now, there's some criteria here that we have to abide by. Even when making an inference from a random sample, it would be very surprising if that estimate was exactly equal to the truth about the population. So we'll learn more about this later on, but you'll notice in stats that's a big theme. Like we never say concrete things and this is exactly the truth type of statements. It's all about the evidence shows that there may be, very vague words. So we have something called sampling variability that we have to talk about in this section. That refers to the fact that different random samples of the same size from the same population will produce different estimates. So what we're going to see today is estimates that are in the form of what's called a proportion, so a ratio or looks like a decimal or even a percentage sometimes. And I might take a sample of 25 from the population and get one proportion, and then go over here and take a different sample of 25 from 25 different candidates and get a different proportion. And the idea is as we move into the inference chapters, if I could do a whole bunch of those samples, I'm going to get closer and closer to the true population um, statistics, which is what we're trying to do. So for today, let's talk about sampling variability and sample size. The idea is the larger your random sample that's the closer it's going to be to the true estimate of the population. So bigger samples are better. That's kind of the idea here. And this is from some example in the book here, but if you have two different samples that you took from, and this first one was a sample size of 20 compared to a sample size of 100, you can see that the data in the 20 sample size is very spread out. And these are percentages. So it ranges anywhere from 10 to 50%, as opposed to a larger sample size of 100. The spread of the percentages here is it's like 22-ish, 22-ish to 40. So it really tightens up the data and gives you less of a range and less variability, which is a concept that we'll come back to when we go look at chapter 1 in a little bit. So here's an example, and I apologize if that's an NFL player. I have no idea who it is. So the NFL players, how much do they weigh on average? So if we sample 50 NFL players, the average weight is 244.4 pounds. Do you feel like that is the true average of the weight of all of the NFL players right now? So, I mean, it could be, but probably not. So if we took a sample size of 50 and then we turned around and took another sample size of 50, a different random sample, it is very, very unlikely that we are going to get 244 pounds again in that new sample. So it's very unlikely that it's going to represent the true average weight of all the NFL players. So the follow-up question there is, which would be more likely to give an estimate that's close to the true value of their average weight if you did a random sample of 50 or a random sample of 100? And the answer is a random sample of 100, because the larger your sample size, the closer to the true population estimate you are. So larger, bigger is better in this case, right? Inference for experiments. So well-designed experiments allow for us to make inferences about cause and effect. And we've talked about what makes a well-designed experiment. And we've also talked about the fact that cause and effect is difficult to prove or conclude in an observational study. But if you have a well-designed experiment, we could use inference to say that we can find a cause and effect. So in an experiment, there are two ways to explain why the average response for one group is different than the other group. Now, the first one basically just says it happened by chance. There was variation in the way that we randomly assigned and pulled our sample, and because of that, we found a little bit of difference, but it's not because of the treatment itself. Now, later in this year, like way later, like chapter 9, 8 or 9, I forget, we're going to talk about something called hypothesis testing when we get into the inference chapters. And this is kind of leading you to what a hypothesis test looks like. So we will definitely revisit this topic. Now, if that difference doesn't happen just by variation in the random assignment, then the difference would be a cause of the treatment. So the actual treatment that you were testing in the experiment is what caused the difference. So you have to decide which one it is. And the key is when the observed results of a study are too unusual to be explained by chance alone. So if number one isn't true, then we say the results are statistically significant, and then we can start making claims like the treatment caused the difference. So this example is interesting. They wanted to know what was more distracting to drivers. So David Strayer at University of Utah designed an experiment to answer this question. They took 48 undergrad students as subjects, and they randomly assigned half of the students to drive in a simulator while talking on a cell phone, and then the other half the remaining half were assigned to talk to a passenger in the simulator. Now the response variable, because they had to test something, was whether or not the driver remembered to stop at the rest area. So they were told ahead of time, like, there's going to be a rest area, you need to pull over and stop there. So were they too distracted by their cell phone or car partner, I guess. So here's the results. And what we're going to do here is we're going to look at the difference in the proportion of students who stopped at the rest area versus the two groups. So the students who were on a cell phone, 12 out of the 24 stopped at the rest area. And the students who were in a car with a passenger that was talking to them, 21 out of the 24 stopped. So just looking at the raw data, you can tell that more people who had just the passenger in the car remembered to stop, right? So if we calculate the difference, passenger minus cell phone in that order, and they changed them to decimals, which you could think of as percents if you'd like. This one was about 0.8, it was 0.875, this one was 0.5. So if you subtracted those, you get a difference in proportions of 0.375 or about, exactly 37.5%. So is that a significant difference? That's the question. Is it significant? Well, for us to answer that, what we have to figure out is whether this difference is just due to chance because of the sampling variability. Now, I apologize, this is really blurry. So this is how they determined whether it was statistically significant. They performed 100 trials of a simulation to see if the difference in proportions would occur due to just chance and variation of the random assignment. So if they assume that the type of distraction did not affect whether they stopped at the rest area, and they just did 100 trials of a simulation. So here's the results. It's in a dot plot. Okay, I'm not going to bother to count it. There's 100 dots here representing those 100 trials. So let me keep reading a little bit here. It says, that is 33 stoppers and 15 non-stoppers were randomly assigned to two groups of 24. So they didn't really take into consideration like who was going to stop at the rest area and who wasn't. Everybody's just back together in one giant group. They performed 100 simulations. And this is what happens when you just leave the variability of the random assignment. Okay. So there's a follow-up question here. It says, there are 3 dots at 0.29. Explain what these dots mean in context. So these 3 dots here are the 0.29. And what that means is for this 100 trials of the simulation, there were 3 trials where the sampling simulated difference, from passenger minus cell phone was 29%. Okay. And you'll notice that is like the tippy top of the scale. There is nothing after 29%. There's nothing after 0.29 for the chance variability. So Let's see if I missed anything there. So the next question is where we start making our conclusion. Use the results of the simulation to determine if the difference from part A is statistically significant. So remember, there's two outcomes. Either the difference happened just by chance because of variability, or the difference happens because of the treatment. So remember, we got a difference of 0.375. And if you go back and look at the simulation, 0.375 isn't even here. So when they did the sampling, the simulation of 100 trials, it didn't even hit 0.375. So the fact that what we got in our experiment lived way out here on this chart and this distribution, that tells us that was pretty significant. That was statistically significant. So book answer here, because the difference of 0.375 or greater never occurred in the simulation, the difference is statistically significant. It is extremely unlikely that we would get a difference this big simply due to chance variation in the random assignment. So option 2 was the correct one here, that no, it didn't just happen because of chance variation in the assignment. It must have happened because of the treatment. So remember, the treatment was having a cell phone versus having a passenger in the car. And obviously we'd have to work on our wording there, but that's the idea. So that is just a really brief intro into what's going to be hypothesis testing eventually and inference over a couple chapters. But like I said, that's happening. Oh gosh, I don't think we'll get it until maybe February. Like it's not for a long time. So we'll revisit that idea. All right, scope of inference. Here's the two big ideas here. The random selection of the individuals allows you to infer about the population. So the fact that we chose the individuals randomly lets us apply this to the population as a whole. But the random assignment to the groups is what allows us to infer about the cause and effect. So both things have to occur. You have to randomly choose people or things or whatever, and you have to randomly assign them for this to work. And this is a handy little chart because if you're trying to figure out what kind of inferences you can make, basically the answer has to be yes to both of those for you to say you can make inferences about both. So if you randomly selected the individuals and you also randomly assigned them to groups, you can make inference about the population and the cause and effect. But here, if you did not randomly select the individuals, but you did randomly assign them to groups, you cannot apply it to the population, but you can make an inference about cause and effect. And you can kind of read through this little matrix and see the different scenarios. So obviously this is what we're hoping for. If we do it right, we're going to be able to make inference about population and cause and effect. So here we have a check your understanding idea. When an athlete suffers a sports-related concussion, does it help to remove the athlete from play immediately? Researchers recruited 95 athletes seeking care for a sports-related concussion at a medical clinic and followed their progress during recovery. Researchers found statistically significant evidence that athletes who were removed from play immediately recovered more quickly, on average, than athletes who continued to play. What conclusions can we draw from this study? Now, first of all, and you can pause the video if you want to write down your own thoughts, but we're going to show the answer in a moment. This is not an experiment, right? This is an observational study. First of all, it would be very unethical to do an experiment on kids who have concussions because I don't even know how you do that. So this is an observational study, which means there's no random assignment or like you're not choosing randomly or assigning anything because it's an observational study. So because these individuals were not randomly selected and it's an observational study, we can only conclude that for the athletes in this study, those who were removed from play immediately recovered more quickly on average than athletes who continued to play. So the scope of inference for this problem is actually very small. It is only applied to those 95 athletes from the study. And it's really doesn't go any farther than that. So not really that impressive of a study. But we do this sometimes in the human media world. We like to pull a study out of nowhere and just throw it out there and see what people like, you know? Hey, I'm not claiming that you should stop playing football after you get a concussion, guys. I think that's pretty obvious, but this is not a well done study, we'll put it that way. Now, The challenges of establishing causation. Oh, that's a funny picture. Um, it's really difficult to establish causation if it's not an experiment. So that last one, remember, was an observational study with the athletes who were getting concussions. You can't make that an experiment because it's unethical, right? We'll talk about that in a moment. So a really great example of an observational study that was able to link to cause and effect, and it's hard to do, but you can do it. Does smoking cause lung cancer? Like that was a big mystery for many, many decades, right? Not in your lifetime so much because before you guys were born, they kind of hit the nail on the head. But the idea is they saw a trend of smokers, lifelong smokers who were developing lung cancer, and they created what you call an association. Okay, so the association was strong. You have statistically high likelihood of someone who smokes developing lung cancer, or possibly the reverse of that. People who developed lung cancer smoked. Now, the association is also consistent. So it wasn't like spotty when they were collecting their data. It was very consistent throughout the decades. They were able to kind of figure out those confounding variables if they could. The larger the value of the explanatory variable are associated with stronger responses. So what they noticed in the smoking observational study over the decades was someone who smoked for decades and decades, or consistently several packs a day, they had a much higher instance of developing lung cancer. So that kind of, you know, made it pretty obvious that there was a connection. And then the alleged cause precedes the effect in time. Now that's a really fancy way of saying like use your noggin here. If you develop lung cancer and then you start smoking afterwards, the smoking did not affect your lung cancer development like at the beginning. So these people had to have been smoking before they developed lung cancer for this to make a connection. And then this one, just really think logically. Is it plausible? You know, there's some weird studies out there. Like, does having red hair make you better at math? Like, no, I don't know. Why would that happen? Like, there's no plausibility there. So it has to be plausible. So in this case, the doctors were saying, yeah, this is entirely plausible. You are smoking chemicals into your lungs, and it is sitting there and rotting and damaging your cells, and you are developing cancer. So yeah, very plausible. So again, there was no experiment happening here. I'm sure there was some sort of horrible experiment that they did on animals, but not on humans. And that is because of data ethics. So it's very important that we kind of follow these because as you guys move on to doing your own experiments, even at Harlem or into college, you have to follow these ethical protocols. So here's the basics. If you're doing a real study, it has to be reviewed in advance by an institutional review board, okay? So when you move on to college, a lot of grad programs, you have to do your own studies. So everything has to be reviewed and approved. All individuals who are subjects in the study must give their informed consent. So we can get some real-time data when we're doing this in class, but like right now as I'm recording this, it is midsummer of 21, and they are currently still performing clinical trials on COVID vaccines for children under 12. Well, the reason that is so slow, well, it's several reasons, but the main one is children cannot consent. Okay? So you have to have a parent who's willing to volunteer their child to get a vaccine. They're trying to kind of figure out what the dosage is. That makes parents kind of nervous. They're not really sure if they want to throw their kid in as a guinea pig. So what you're finding is a lot of the children that are being utilized in these trials right now are children of medical professionals. So I'm not saying that's good or bad. I'm just saying that's where we're at. So informed consent. So if it's a child, that makes it a little more complicated. And individual data, all individual data, excuse me, must be kept confidential. When you show your results, you can't say like, here's John's results, and here you see his weight, and here you are. There's no names, no figures, no ID numbers associated. You can only give statistical summaries of the group itself. So we'll talk more about that if we ever try to design our own experiments, which we will. The good news is you guys aren't going to do anything such high stakes where it's terrible and you have to like really think about it, but just use common knowledge. No one can perform unethical experiments at any point, whether you're in high school, college, or beyond. All right, there's our learning targets. That must mean we're done. So just to reiterate, guys, that question about simulation and inference and, we're going to keep it real basic as we test you on those ideas this chapter because we have a lot other things to learn before we move on and make statistically significant claims. All right, we're not there yet. I just want to give you kind of the basics of it. All right, I appreciate your time. Good luck, everybody.